Hello everyone, this is Group 14 and this is our presentation for the semester project Big Screen. In this presentation, we will cover the essential parts of this project, the mentality we kept during the development, the core parts of the projects, front-end, backend, and cloud, and the summary for everything that we will describe. Going into this semester project, our team had a mentality and key points we wanted to focus on. The project served as a sandbox before the bachelor's project, a project where we can get all of our team members on the same page using the same kinds of technologies, sharing the same vision. We heavily focused on making our code as generic as possible so we can reuse it in the project itself or in the future projects as well. Having our code generic and following solid principles goes hand in hand. We didn't want any manual processes in our team, therefore we agreed to automate as many flows as possible. This ensured consistency and efficiency. The team focused on a smart management of our Azure resources and service plans, so we don't have to cover any unwanted expenses. Our process was key to a successful semester project. We kept our board clean, refined, and had the necessary meetings to add or modify items to backlog. There are three main topics when we speak about big screen frontend. It's the user interface, model view model, architectural pattern, and API clients. The graphical user interface is based on the Material Design System guidelines. This ensures a consistent UI where we, as developers, don't have to think about how a button should look like because other design experts figured it out for us, and we just have to use it. The general layout of the application was inspired by other online movie databases, for example, IMDb and the movie database. It served as a shortcut for deciding how to position data on our pages. Blazor WebAssembly was used as the front-end framework. The main reasons for choosing Blazor was that the team was already familiar with this technology, so we didn't have to waste time on learning a JavaScript framework. Also, we could share code with the backend, for example, our models for ratings, comments, DTOs, and so on. We used a component library called MudBlazor. This library is built on top of the material design, hence we got advanced components like dropdowns, drawers, progress bars with the right material design styling out of the box. Model view model is an architectural pattern that we've implemented on the front end. The main reasons for that were to detach presentation layer from the data layer, because there are heavy logical or networking operations that might occur on the data layer, so they don't affect the view. This architectural pattern assisted us with ensuring that the responsibility of different modules is separated. View, from the picture represents the Razor and the component base files, is responsible for displaying data. The Razor file contains the Razor syntax and HTML, while the component C# file opens up for parameters and overrides Blazor lifecycle methods. The view gets and sets data from the view model, and the view model is the place where a lot of logic is done, so it provides the view with the valuable and right information for the users. The view model gets and sets data from handlers that are calling different clients to retrieve or store data to various data sources. The front end consumes information related to the film industry from the TMDB API. The API is being called directly in the front end, so there aren't any extra expenses for the backend computing time and also to avoid calling multiple requests instead of one. The backend API client is a generic OData client. The client is able to consume data from any API that implements OData protocol. This enables reusing this code in future if the frontend will be connected to another API. Next, Avrimas will present how backend is structured.
Thank you, Alex. A big screen SDK was developed to be used throughout the project. It contains OData controllers, data access, and database sets which are relevant for the backend. A data controller acts as any other API controller. It exposes an endpoint and handles incoming HTTP requests. What OData, also known as the Open Data Protocol, differs from regular controllers is that it offers a uniform way to query and manipulate datasets through CRUD operations. OData offers multiple ways of querying data, adding limitations or reducing the payload size. But most importantly, it allows data aggregation within a query and does not require any code added to the backend for these requests. It is easier to understand OData with an example, so let me give you a few examples of how OData was used in Big Screen. First, it was allowed to request data and get it all with expand option. Expand allowed retrieval of data transfer object with nested objects. If the client only needed a single attribute or subset of properties, a select option was exposed, which allowed getting only the username or a list of movies showing only the name. For the second example, let's talk about OData filter option. It filters the result based on certain conditions, like adding a where clause, if you will. In Big Screen, the users can see average scores for movies or TV shows. The filter option allowed creating an aggregation pipeline in the query, grouping all the scores for media type, adding the sum of these scores, and returning the average score. Talking about controllers and backend in general, it is important to mention that the backend does not use concrete classes, but rather has generic type implementations. Using generic classes allowed elements to be reused, which resulted in clean and maintainable code without duplication. This brings me to another segment in the presentation, data access. After a request is made to the controller, a data transfer object is passed to the data access instance. Since dealing with generics, there's a data access instance for every controller. These instances are retrieved via dependency injection. The purpose of data access is to convert requests that come with a data transfer object to a request that has a database entry and vice versa. Since generics are in play, it was important to find a way how object conversion can be achieved without manually going through every entity. The solution was to use the AutoMapper library, which allowed a two-way mapping. So to recap, a request is made to a controller, then the data transfer object is converted to a database entry object in data access. After this, the data is sent to the database set, also known as collection. A database set retrieves a connection to a container and then enables CRUD operations to be executed on that container. The collection is retrieved by a Cosmos database connector, which is added by a Cosmos database builder. This Cosmos database builder is also adding the database sets as services. A database set is also responsible for checking the E tag, checking that an item exists, or checking that if an item is created with a custom ID, the ID is unique and meets the GUID format. An E tag or entity tag is used to validate that the client has the most recent version of the record. It is used to ensure data integrity, that newer data is not overwritten accidentally by old data. After an operation is performed on a database set, the response is sent back to the data access. Conversion from database entry to data transfer object is performed, and the data is sent back to the client through the OData controller. A database set is also responsible for throwing appropriate exceptions if needed. When exceptions are caught, relevant response codes are sent to the client. This concludes the backend part of the project, and now Paul will talk about all things cloud.
Thank you, Auri. Our cloud provider of choice was Microsoft Azure, as most of our total cloud experience as a group is within Azure, and it also allowed us to integrate our working processes with it. The following information is also present in the cloud guide, where it is much more detailed. Let's start with the cloud resources, of which we have a few within our own Azure Active Directory tenant. We have an app service plan, which has a client app service and an API app service. We have a Cosmos database instance, we have a Key Vault, and we have an Azure Active Directory Business to Customer, which is a different tenant as a resource. App services are serverless environments to host web anything, web apps, web APIs, websites, web stuff in general that should be available through an internet address. We have two app services, one for the web client and one for the web API, both of which are part of the same app service plan. An app service plan is the performance plan the apps are running on. The performance tiers can go from free to a full paycheck, and the usage is billed per compute hour. The production tiers also support autoscale, so the available resources adjust according to demand, this being a big benefit of the cloud in general. The development plans have usage quotas. While developing, ours have been running on a development-free F1 plan so we can test the deployments, but they have been since promoted to run on the cheapest one that's not free, the D1 plan, which has higher quotas. It is not a production plan, so it is still somewhat slow. One thing to note performance-wise on the development plan is that these apps are put to sleep after some time if they are unused, and as such, when accessing the app for the first time in a while, it will be a bit sluggish until it wakes up due to our performance plan. The client has a benefit as all the code is cached on the actual client, so after starting it once, it will be fast every time a user accesses it after until they clear the browser cache, but interactions with our own API will be slow until it wakes up. Then Cosmos DB, it is a document-based NoSQL database. It has a well-documented C# SDK and an emulator, which allowed us to easily use it code-wise and be able to run tests locally and in the pipelines without depending on a cloud resource. Cosmos DB has two performance plans, provision throughput and serverless, the difference being well documented by Microsoft themselves. We are using the serverless option since this project is not expected to have a lot of traffic. The connection string to the Cosmos DB instance is stored in a key vault, which is a secret management resource. In the key vault we can put secrets, certificates and keys that we want to be kept secret. We are using this so we don't have a connection string in our code which is now public on GitHub. The access to the key vault is restricted with Azure Identity by setting access policies for different entries from the Active Directory tenant. In order to give access to apps, the app service instances have a system-assigned identity, which makes the members of the AD just like actual humans. The apps can then authorize themselves to get secrets out of the key vault. Then there's Active Directory overall. We have our own AD tenant, a normal instance in which the group members are invited, the resources are hosted, and the subscriptions are billed. This is off limits to anyone that's not part of the tenant. Let's call this Big AD. Then there is an Azure Active Directory business to customer, which I'm just going to refer to as AD B2C, used for authentication within Big Screen itself, and which is a resource group within the Big AD on the same subscription as the other resources. This is where we manage the users of Big Screen. There are no cloud resources in this tenant, only users and authentication related stuff, and it allows us to add new identity providers such as Google and Facebook with no extra code. It also handles email and password authentication, so the user's data security is Microsoft's concern. DevOps wise, we have used Azure DevOps, which allows us to have a Kanban board since we used Kanban for this project. Git repository and pipelines all linked together with connections to Azure Cloud. This is also explained in the cloud guide with some nice pictures as well. So to sum up, we have used Blazor WebAssembly for our web client, which executes all code on the client machine. We also used the MudBlazor component library to make it pretty. We delegated as much work as possible to TMDB, reducing our own computing costs. We focused on making as many generic, plug-and-play, reusable components, both on the client and on the API, to avoid duplicating code. For the backend, this resulted in the Big Screen SDK, allowing us to build any web API and easily extend the Big Screen API itself. All of this is running in Azure, both the services and our process. Thank you for watching. This was Group 14 with Big Screen, and have a nice summer.